Grounding and bonding are critical for the safety and functionality of a detached additions electrical system. Firstly, let's discuss the UFER ground. The UFER ground, which is an electrode encased in concrete, should be bonded to the grounding electrode system, also called the GES, at the main service panel in the house. This is typically achieved using a grounding electrode conductor, also known as GEC, that runs from the UFER ground to the main panel. The grounding electrode conductor ensures a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Secondly, consider the ground rod. The ground rod at the addition should also be bonded to the grounding electrode system at the main panel. This can be done with a separate grounding electrode conductor or by running the grounding electrode conductor from the UFER ground to the ground rod and then to the main panel. The purpose of the ground rod is to provide an additional grounding point, especially important in areas with high soil resistivity. The connection of both the UFER ground and the ground rod to the main panel ensures a robust grounding system. Now let's move on to bonding. Bonding involves connecting metallic parts together to create an electrically conductive path. This minimizes voltage differences and reduces the risk of electric shock. The cold water line at the exterior water entrance should be bonded to the ground rod. This bond should be made with the UL-listed grounding clamp to ensure a secure and reliable connection. The grounding clamp should be installed in an accessible location and be protected from physical damage. The purpose of bonding the cold water line is to provide a path for fault current to flow back to the source, helping to trip the circuit breaker in the event of a fault. Next, the gas line should be bonded to the cold water line. This bond should also be made with a UL-listed grounding clamp. It's important to bond the gas line to prevent it from becoming energized in the event of an electrical fault. The bonding of the gas line reduces the risk of ignition of flammable gases in the event of a fault. The cold and hot water lines of the water heater should be bonded to the grounding terminal of the water heater. A bonding strap or jumper should be used to make this connection. This is essential to prevent any potential voltage differences between the water pipes and the water heater, which could create a shock hazard. The bonding should be made with a lower impedance path to ensure effective fault current conduction. Now let's consider additional factors. All electrical equipment in the addition should be properly grounded. This includes outlets, light fixtures, and appliances. The grounding conductor should be connected to the grounding bar in the electrical panel. Equipment grounding provides a safe path for fault current to return to the source, protecting individuals from electric shock and preventing damage to equipment. If the addition is in a lightning-prone area, consider installing a lightning protection system. This will help to protect the electrical system and equipment from lightning strikes. Lightning protection systems typically consist of air terminals, conductors, and grounding electrodes. The system provides a path for lightning current to flow to ground, minimizing the risk of damage to the structure and its contents. Now let's discuss some recommended adjustments. Instead of bonding the ground rod to the UFER ground and then to the ground rod, it is recommended to bond the ground rod directly to the grounding electrode system at the main panel. This provides a more direct path to ground. A direct connection to the main panel ensures a lower impedance path for fault current, improving the effectiveness of the grounding system. Let's talk about grounding conductor sizing. The grounding electrode conductor should be sized appropriately based on the amperage rating of the electrical service. For example, a 100 amp service would require a 6 American wire gauge or AUG grounding electrode conductor. The size of the grounding electrode conductor is determined by the National Electrical Code, or NEC, Table 250.66, which specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It's crucial to use the correct size grounding electrode conductor to ensure that it can safely carry fault current. Consider a scenario where you have a 200 amp service. In this case, you would need a larger grounding electrode conductor, typically a 4 American wire gauge or AUG copper conductor. Always consult the National Electrical Code, or NEC, Table 250.66 to determine the correct size grounding electrode conductor for your specific service. Improperly sized grounding electrode conductors can lead to inadequate protection and increase the risk of electrical hazards. It's also important to ensure that all grounding and bonding connections are made properly and are mechanically secure. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. Use appropriate connectors and tools to make the connections and inspect them regularly to ensure that they are in good condition. In addition to the grounding electrode conductor, it's also important to ensure that the equipment grounding conductors are properly sized. The equipment grounding conductors provide a path for fault current to return to the source from electrical equipment such as outlets, light fixtures, and appliances. The size of the equipment grounding conductors is determined by the size of the overcurrent protective device protecting the circuit, as specified in the National Electrical Code, or NEC, Table 250.122. For example, a 20-amp circuit would typically require a 12 American wire gauge, or AUG, equipment grounding conductor. It's essential to use the correct size equipment grounding conductor to ensure that it can safely carry fault current and protect equipment and personnel. In some cases, it may be necessary to use a larger equipment grounding conductor than what is required by the National Electrical Code, or NEC, especially in situations where there is a long circuit run or where the impedance of the grounding path is high. This is often referred to as an increased size or supplemental equipment grounding conductor. The decision to use a larger equipment grounding conductor should be based on engineering calculations and consideration of the specific installation conditions. Proper grounding and bonding are essential for the safe and reliable operation of any electrical system. By following the guidelines and recommendations outlined, you can help ensure that the detached addition is properly grounded and bonded, providing a safe and functional electrical system. Remember to always consult the National Electrical Code, or NEC, and local electrical codes for specific requirements and to obtain the necessary permits and inspections. It's also recommended to hire a qualified electrician to perform the grounding and bonding work to ensure that it is done correctly and safely. Electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. In addition to the points already discussed, it's worth noting that the National Electrical Code, or NEC, has specific requirements for the types of grounding and bonding conductors that can be used. For example, the grounding electrode conductor must be made of copper, aluminum, or copper-clad aluminum and must be installed in a manner that protects it from physical damage. The equipment grounding conductors must be made of copper or aluminum and must be identified by a continuous green color or a green color with one or more yellow stripes. It's important to use the correct types of conductors for grounding and bonding to ensure that they meet the requirements of the National Electrical Code, or NEC, and provide adequate protection. Also, remember that the grounding electrode system should be tested periodically to ensure that it is functioning properly. This can be done by measuring the resistance to ground of the grounding electrode system. A low resistance to ground indicates a good grounding system, while a high resistance to ground indicates a problem that needs to be addressed. The National Electrical Code, or NEC, recommends that the resistance to ground of the grounding electrode system should not exceed 25 ohms. If the resistance to ground is higher than 25 ohms, it may be necessary to install additional grounding electrodes or to improve the existing grounding electrodes. It's also important to ensure that the grounding electrode system is protected from corrosion. Corrosion can increase the resistance of the grounding electrode system and reduce its effectiveness. To protect the grounding electrode system from corrosion, it may be necessary to use corrosion-resistant materials or to apply a protective coating to the grounding electrodes. Finally, remember that grounding and bonding are not the same thing. Grounding is the connection of the electrical system to the earth, while bonding is the connection of metallic parts together to create an electrically conductive path. Both grounding and bonding are essential for the safe and reliable operation of any electrical system, and they should be performed in accordance with the requirements of the National Electrical Code, or NEC, and local electrical codes. By following these guidelines and recommendations, you can help ensure that the detached addition is properly grounded and bonded, providing a safe and functional electrical system for years to come. Always remember to prioritize safety when working with electricity and consult with a qualified electrician if you have any questions or concerns. By adhering to these best practices, you can minimize the risk of electrical hazards and ensure the well-being of yourself and others. In addition to the grounding electrode conductor and equipment grounding conductors, it's also important to consider the bonding jumpers. Bonding jumpers are used to connect metallic parts together to create an electrically conductive path. They are typically used to bond metal water pipes, gas pipes, and other metallic components to the grounding system. The size of the bonding jumpers is determined by the size of the circuit that is likely to energize the metallic component, as specified in the National Electrical Code, or NEC, Table 250.102. For example, a circuit that is likely to energize a metal water pipe would require a bonding jumper that is sized according to the National Electrical Code, or NEC, Table 250.102. It's essential to use the correct size bonding jumpers to ensure that they can safely carry fault current and provide a low impedance path for fault current to return to the source. Bonding jumpers should be made of copper or aluminum and should be installed in a manner that protects them from physical damage. They should also be securely connected to the metallic components using appropriate connectors. When installing bonding jumpers, it's important to avoid creating ground loops. Ground loops occur when there are multiple paths for ground current to flow, which can create unwanted circulating currents and increase the risk of electrical noise. To avoid ground loops, it's important to bond all metallic components to a single grounding point. This will ensure that there is only one path for ground current to flow and minimize the risk of circulating currents. In addition to the bonding jumpers, it's also important to consider the surge protection. Surge protection devices, also known as surge suppressors, are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line disturbances. Surge protection devices are typically installed at the main electrical panel and at individual electrical outlets. They work by diverting the surge current to ground, protecting the electrical equipment from damage. It's important to choose surge protection devices that are rated for the voltage and current of the electrical system and that meet the requirements of the National Electrical Code, or NEC. Surge protection devices should be installed in accordance with the manufacturer's instructions and should be inspected periodically to ensure that they are functioning properly. In addition to the electrical grounding and bonding, it's also important to consider the structural grounding and bonding. Structural grounding and bonding is the connection of the metallic parts of the building structure to the grounding system. This includes metal framing, metal siding, and metal roofing. The purpose of structural grounding and bonding is to provide a path for lightning current to flow to ground and to minimize the risk of fire and electric shock. Structural grounding and bonding should be performed in accordance with the requirements of the National Electrical Code, or NEC, and local building codes. It's important to consult with a qualified electrician or engineer to determine the specific requirements for structural grounding and bonding in your area. Finally, remember that electrical safety is an ongoing process. It's important to inspect the electrical system regularly to identify and correct any potential hazards. This includes checking for loose connections, damaged wiring, and overloaded circuits. It's also important to educate yourself and others about electrical safety and to follow safe work practices when working with electricity. By taking these precautions, you can help ensure the safety of yourself, your family, and your property.